November 15, 1944, Peleliu Island, Pacific Theater. The morning sun cast long shadows across the coral ridges as 18-year-old Private Marcus Washington crouched behind a shattered palm tree, his Browning M19-19A4 machine gun silent and useless beside him. The weapon that had sustained his squad through 3 weeks of relentless fighting now mocked him with its jammed mechanism, while enemy positions remained active just 200 yards ahead. What Washington believed would be another routine suppression mission was about to become something neither he nor his commanding officers could have ever imagined. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. This is the extraordinary account of how desperate circumstances, basic field rations, and the ingenuity of a young Marine from Detroit would transform a mechanical failure into an improvised weapon that defied every conventional rule of warfare. Private Marcus Washington had enlisted in the United States Marine Corps 6 months after his 18th birthday, carrying with him the determination of someone who had watched his older brother return from the European theater with stories that seemed impossible to believe. Growing up in Detroit's industrial heart had given Washington an intuitive understanding of machinery that would prove invaluable on this remote Pacific island. His hands, calloused from summer jobs in automotive factories, possessed the kind of practical knowledge that military training manuals could never fully teach. The 3rd Battalion, 27th Marines had landed on Peleliu as part of Operation Stalemate 2, an amphibious assault that military planners estimated would require 3 days to complete. 3 weeks later, they were still fighting for every yard of coral and sand against an enemy that had transformed the island into a fortress of interconnected caves and tunnels. Washington's machine gun section had become essential to their advance, providing covering fire that allowed rifle squads to move between the jagged ridgelines that dominated this hellish landscape. Sergeant Thomas Mitchell, a veteran of Guadalcanal and Bougainville, had personally selected Washington for his machine gun crew after observing the young Marine's mechanical aptitude during training exercises at Camp Pendleton. Mitchell recognized something in Washington that went beyond standard military competence, an ability to see solutions where others saw only problems. This intuition would prove prophetic on a morning when conventional weapons failed and improvisation became a matter of survival. The machine gun that now lay silent beside Washington represented the pinnacle of American small arms manufacturing. The Browning M19-19A4 fired .30 caliber ammunition at a rate of 400 to 600 rounds per minute, with an effective range that could reach 1,500 yards under optimal conditions. Each weapon weighed 31 pounds without its tripod mount and required a crew of 2 to operate effectively. Washington had memorized every component, every maintenance procedure, and every technical specification during his months of training. But technical specifications meant nothing when the weapon refused to function. The morning's firefight had begun routinely enough. Enemy positions had opened up with small arms fire from concealed positions among the coral formations, and Washington's machine gun had responded with measured bursts designed to suppress their activity. The rhythm of combat had become familiar after weeks of similar engagements. Short bursts to conserve ammunition, steady pressure to keep enemy forces pinned down, coordination with rifle squads who would advance under cover of the suppressing fire. The jam had occurred during the 4th sustained burst of the engagement. Washington felt the weapon's rhythm falter, heard the mechanical hesitation that every machine gunner learned to recognize as the harbinger of malfunction. The bolt had failed to fully cycle, leaving a cartridge partially extracted from the chamber while simultaneously attempting to feed another round from the ammunition belt. This type of double feed represented one of the most serious malfunctions possible in a belt-fed weapon, requiring disassembly that could take precious minutes under combat conditions. Washington's assistant gunner, Private First Class Roberto Santos from El Paso, Texas, immediately began the standard malfunction procedure while Washington maintained observation of the target area. Santos had trained extensively on weapons maintenance and could disassemble the machine gun's major components in under 2 minutes during peacetime conditions. But combat introduced variables that training exercises could never fully replicate. The stress of incoming fire, the urgency of tactical situations, and the psychological pressure of knowing that friendly forces depended on their weapons' function. The attempted repair revealed a problem that went beyond standard field maintenance capabilities. The cartridge case had not merely failed to extract cleanly, it had ruptured inside the chamber, leaving brass fragments wedged in locations that field tools could not reach. The bolt itself showed signs of damage that suggested metal fatigue from weeks of intensive use. Combat conditions on Peleliu had pushed every piece of equipment beyond its designed operational limits, and Washington's machine gun had finally succumbed to the accumulated stress of continuous fighting. Sergeant Mitchell arrived at Washington's position as Santos completed his assessment of the weapon's condition. The sergeant's weathered face showed no surprise at the news of the malfunction. He had seen enough combat to expect equipment failures at the most critical moments. Mitchell's immediate concern focused on maintaining fire support for the rifle squad that was attempting to advance through a gap in the coral formations. Without the machine gun suppressing fire, that advance would become impossible to sustain. "How long for a complete rebuild?" Mitchell asked Santos, though his tone suggested he already knew the answer would be unacceptable. Santos looked up from the disassembled weapon components scattered across his shelter half. "At least 30 minutes, Sergeant. Maybe longer if we can't clear those brass fragments without proper tools." Mitchell nodded grimly and turned his attention to Washington. "Ideas, Private? Your people back in Detroit ever deal with jammed machinery?" Washington had been studying the tactical situation while Santos worked on the weapon. The enemy positions were located in a series of coral caves that formed natural defensive positions approximately 200 yards from their current location. The cave's openings faced directly toward the route that their rifle squad needed to use for their advance, creating an interlocking field of fire that would be devastating without suppression. Conventional infantry weapons lacked the range and sustained fire capability needed to keep those positions neutralized for the duration of an assault. But Washington had noticed something else during his observation of the target area. The coral formations that protected the enemy positions also created a natural funnel effect that concentrated airflow in specific directions. The morning breeze, consistent and steady from the northeast, would carry anything airborne directly into those cave openings. This observation triggered a memory from Washington's childhood in Detroit, where he had watched workers at a foundry use directed heat to clear blockages from machinery. Washington's field pack contained the standard allotment of C-Rations that every Marine carried during combat operations. These individual meal packages included items that seemed mundane in comparison to military weapons and equipment. But Washington began to see them through the lens of industrial problem-solving. Each C-Ration pack contained fuel tablets designed for heating meals in small portable stoves. These hexamine fuel tablets burned at extremely high temperatures and produced intense, sustained heat when ignited. The mechanical components of the jammed machine gun, while useless for their intended purpose, could potentially serve as the framework for an entirely different type of weapon. The gun's tripod provided a stable mounting platform. The barrel, despite its damaged chamber, remained structurally sound and could serve as a launching tube. The weapon's traversing and elevating mechanism still functioned perfectly, allowing for precise targeting of distant positions. Washington began gathering materials from his personal equipment and from the disabled machine gun components. He removed 12 hexamine fuel tablets from various C-Ration packages, carefully scraping the material into powder form using his combat knife. The powder retained all the combustible properties of the original tablets, but would burn much more rapidly when ignited in an open container. This rapid burn rate would be essential for creating the pressure needed to launch projectiles over the required distance. Santos watched Washington's preparation with growing understanding. "You're thinking like a mortar, aren't you? Use the barrel as a launch tube?" Washington nodded while continuing his methodical preparation of materials. "Something like that. But we need more than just explosive force. We need sustained burning that will clear those cave positions." The solution came from another component of the C-Ration system. Each meal package included a small can of processed meat suspended in heavy grease. This grease, designed to preserve the meat during long storage periods, possessed properties that made it ideal for incendiary applications. It would burn slowly and steadily once ignited, producing intense heat that would persist long after the initial fuel explosion. Combined with the hexamine powder, it could create an improvised incendiary mixture that would serve as an effective area denial weapon. Washington removed the meat from 3 C-ration cans and set it aside for later consumption, keeping only the thick grease that coated the interior surfaces. He mixed this grease with the powdered hexamine fuel, creating a sticky, combustible paste that would adhere to surfaces and burn for extended periods. The mixture reminded him of materials he had seen used in Detroit foundries for metalworking applications, though those industrial processes used much more sophisticated compounds. The delivery system required more improvisation. Washington needed containers that could hold the incendiary mixture while surviving the launch process, then break apart on impact to distribute the burning material effectively. The answer came from equipment that every Marine carried: fragmentation grenades. Not for their explosive properties, which would be inappropriate for this application, but for their metal casings, which could be modified to serve as incendiary projectiles. Washington carefully removed the explosive charges from 3 Mark II fragmentation grenades, keeping only the segmented metal casings that gave these weapons their distinctive appearance. Each casing could hold a substantial amount of the incendiary mixture, while maintaining enough structural integrity to survive launching from the machine gun barrel. The segmented construction would ensure that the casings broke apart on impact, distributing the burning grease mixture across a wide area. The launching mechanism presented the most complex engineering challenge. Washington needed to create enough pressure to propel the improvised projectiles over a distance of 200 yards, while ensuring that the force was applied gradually enough to avoid destroying the projectiles during launch. The machine gun barrel's rifling, designed to impart spin to bullets, would actually work against this application by creating excessive stress on the improvised projectiles. Washington solved this problem by creating a smoothbore launch system within the existing rifle barrel. He used cleaning patches and medical tape to create a protective sleeve that would center the projectiles within the barrel, while preventing them from engaging the rifling. This sleeve system would allow the projectiles to travel through the barrel without spinning, reducing the mechanical stress that might cause them to break apart during launch. The propellant charge required precise calculation to achieve the necessary range without overpressurizing the improvised system. Washington had observed mortar crews during training exercises and understood the relationship between propellant quantity and projectile range. He experimented with different combinations of hexamine fuel tablets, testing small charges outside the barrel to gauge their explosive force. After several tests, he determined that 2 fuel tablets, crushed and mixed with a small amount of water to create a more controlled burn rate, would provide adequate propulsion. Sergeant Mitchell had been monitoring Washington's progress while coordinating with the rifle squad that remained pinned down by enemy fire. The sergeant's combat experience had taught him to recognize innovative solutions, even when they defied conventional military procedures. Mitchell understood that desperate circumstances often produced the most effective tactical innovations, and Washington's methodical approach suggested genuine engineering competence rather than reckless improvisation. "You really think this contraption will work, Washington?" Mitchell asked as he examined the modified machine gun assembly. Washington looked up from his final preparations, his hands steady despite the adrenaline coursing through his system. "Sergeant, I've seen similar principles work in industrial applications back home. The physics should be sound, and we've got the materials to make it happen." Mitchell nodded slowly. The rifle squad needed suppressing fire within the next 10 minutes, or their advance would have to be called off entirely. Conventional options had been exhausted, and Washington's improvised weapon represented their only remaining tactical alternative. "All right, Private. Show me how this thing works." Washington positioned the modified machine gun on its original tripod mount, adjusting the elevation and azimuth controls to target the primary enemy cave position. The weapon's original sighting system remained functional, allowing for precise aiming, despite the unconventional nature of the projectiles. Washington loaded the first improvised projectile into the barrel, followed by the calculated propellant charge positioned behind it. The ignition system used the machine gun's original firing mechanism, modified to ignite the hexamine propellant rather than strike a cartridge primer. Washington had rewired the firing pin assembly to include a piece of magnesium ribbon taken from a signal flare. When the trigger was pulled, the firing pin would strike the magnesium, creating intense heat that would instantly ignite the propellant charge. Washington aimed carefully at the largest cave opening, which intelligence reports indicated contained at least 3 enemy positions capable of interdicting the planned advance route. The range was approximately 210 yards, with a slight upward angle due to the elevated nature of the target. Washington adjusted the weapon's elevation accordingly, using his understanding of ballistic trajectories gained from machine gun training. "Firing," Washington announced, following standard range safety procedures despite the unconventional nature of the weapon. The improvised launcher produced a deep, hollow thump as the propellant charge ignited. The projectile emerged from the barrel with a visible trail of smoke, following a high arc through the morning air. Washington and his team watched as the projectile reached the apex of its trajectory and began to descend toward the target area. The flight time was approximately 4 seconds, during which enemy fire from the targeted position continued uninterrupted. The impact occurred precisely at the cave mouth Washington had targeted. The improvised projectile struck the coral formation and broke apart as designed, distributing burning grease mixture across the cave opening and the surrounding area. The incendiary material immediately began producing thick, white smoke that billowed into the cave system. Within seconds, the smoke was followed by visible flames as the grease mixture achieved full combustion. The effect on enemy fire from that position was immediate and dramatic. The sustained automatic fire that had been emanating from the cave ceased abruptly as the defenders were forced to retreat deeper into the tunnel system to escape the smoke and heat. Washington observed the target area through his rifle scope and confirmed that no muzzle flashes were visible from the treated position. Santos had already prepared the second projectile, while Washington fired the first. The assistant gunner's efficiency reflected hours of training in rapid reload procedures, adapted now to this unconventional weapon system. Washington adjusted his aim to target the second cave position, which was located approximately 30 yards to the left of the first target. This position had been providing flanking fire that would threaten the rifle squad's planned advance route. The second shot followed the same trajectory profile as the first, with minor adjustments for the different target location. Washington's aim proved equally accurate, and the incendiary projectile delivered its payload directly into the cave opening. The burning grease mixture produced the same suppressive effect, forcing enemy defenders to abandon their positions and retreat into the tunnel network. Sergeant Mitchell used his field radio to coordinate with the rifle squad, confirming that the suppression was adequate for their advance to proceed. Lieutenant James Harrison, the platoon commander, acknowledged the effectiveness of Washington's improvised weapon system and requested continued fire support to maintain suppression during the assault phase of the operation. Washington fired the third and final projectile at the remaining enemy position, achieving another direct hit that effectively neutralized the defensive fire from that location. The 3 incendiary strikes had created a curtain of smoke and flame across the entire enemy defensive line, providing the rifle squad with the opportunity they needed to advance through the gap in the coral formations. The rifle squad's advance proceeded without opposition from the previously active enemy positions. The Marines reached their objective, a strategic ridgeline that would allow them to observe and control the next phase of the battalion's advance. The success of this tactical movement would enable the entire company to continue their push toward the island's interior, bringing them measurably closer to completing their mission on Peleliu. Lieutenant Harrison approached Washington's position as the rifle squad consolidated their hold on the newly captured terrain. The lieutenant, a college graduate from Virginia who had earned his commission through Officer Candidate School, possessed sufficient technical background to understand the engineering principles behind Washington's improvised weapon system. "Private Washington," Lieutenant Harrison said, as he examined the modified machine gun assembly, "I need you to document exactly how you built this system. We're going to want to share this technique with other units." Washington spent the next hour creating detailed notes and sketches that explained the construction process. material requirements and operational procedures for his improvised incendiary launcher. His documentation included safety warnings about proper handling of the hexamine fuel and recommendations for minimum safe distances during firing operations. The technical manual he produced would eventually be distributed to machine gun sections throughout the Pacific Theater. The immediate tactical success of Washington's innovation had broader implications for the battalion's operations on Peleliu. The cave positions that his improvised weapon had neutralized would have required significantly more time and resources to clear using conventional assault techniques. Infantry assaults against prepared cave positions typically resulted in substantial casualties and consumed enormous quantities of ammunition and explosives. Colonel Henry Peterson, the battalion commander, visited Washington's position later that afternoon to personally observe a demonstration of the improvised weapon system. Peterson, a professional Marine officer with extensive pre-war experience, recognized the potential applications of Washington's technique for the types of cave warfare that dominated fighting throughout the Pacific Islands. "Private," Colonel Peterson said, after watching Washington prepare and fire a demonstration shot, "You've just revolutionized how we're going to approach cave clearance operations. This technique could save hundreds of Marine lives over the course of this campaign." Washington's innovation arrived at a critical moment in the Pacific War when American forces were encountering increasingly sophisticated enemy defensive positions. The island-hopping strategy that characterized the Pacific Campaign required American forces to assault heavily fortified positions that had been prepared over months or years. Traditional assault techniques, while effective, came at enormous human and material costs that threatened the sustainability of the offensive campaign. The improvised incendiary launcher addressed specific tactical problems that conventional weapons could not solve effectively. Cave positions were naturally resistant to artillery bombardment and air attacks, which often failed to penetrate deep enough into tunnel systems to neutralize defenders. Infantry assaults against such positions required close-range combat that typically resulted in heavy casualties among attacking forces. Washington's system provided a middle ground between ineffective long-range bombardment and costly close-range assault. The incendiary projectiles could be launched from safe distances while delivering sustained suppressive effects that forced enemy defenders to abandon their positions temporarily. This temporary suppression created opportunities for conventional forces to advance without facing the full defensive potential of prepared positions. News of Washington's innovation spread rapidly through the Marine Corps communication networks that connected units across the Pacific Theater. Technical intelligence officers documented the system's specifications and forwarded them to research and development facilities in the United States, where engineers began developing improved versions using purpose-built components rather than improvised materials. The Marine Corps Equipment Board initiated a formal evaluation of incendiary launcher systems based on Washington's field innovation. This evaluation process involved testing various projectile designs, propellant compositions, and delivery systems to determine the most effective configuration for production weapons. The board's work would eventually result in the adoption of improved incendiary weapons that incorporated the principles Washington had discovered through necessity. Washington's personal experience with his improvised weapons system continued throughout the remainder of the Peleliu campaign. His machine gun section was specifically tasked with cave suppression missions that allowed other units to advance more rapidly through the island's defensive positions. The success of these missions contributed significantly to the battalion's ability to complete their assigned objectives ahead of schedule. The psychological impact of the incendiary attacks proved as important as their tactical effectiveness. Enemy defenders who experienced the suppressive effects of burning grease and choking smoke often abandoned positions that might otherwise have been defended to the last man. This psychological effect reduced the intensity of resistance that American forces encountered during subsequent operations, contributing to lower casualty rates across the entire campaign. Private First Class Santos became an expert operator of the improvised launcher system, developing techniques for rapid projectile preparation and accurate fire control. Santos documented his operational procedures in a field manual that complemented Washington's technical documentation. Together, these documents provided complete instructions that allowed other machine gun sections to replicate the system using locally available materials. The improvised launcher's effectiveness led to its adoption by other units within the 3rd Battalion, and eventually by Marine forces throughout the Pacific Theater. Each unit adapted the basic design to incorporate locally available materials and address specific tactical requirements. This grassroots innovation network demonstrated the Marine Corps' ability to rapidly disseminate and improve upon field innovations. Sergeant Mitchell submitted a formal recommendation that Washington be considered for decoration in recognition of his innovation under combat conditions. Mitchell's recommendation emphasized not only the tactical effectiveness of Washington's invention, but also its broader impact on Marine Corps operational capabilities. The recommendation noted that Washington's quick thinking and technical competence had saved lives and accelerated mission completion. The maintenance requirements for Washington's improvised system proved manageable even under field conditions. The basic components, machine gun tripod, modified barrel, and improvised projectiles, could be serviced and repaired using standard infantry tools and materials. This maintainability ensured that the system remained operational throughout extended combat operations without requiring specialized support. Washington's success with improvised weapons led to his assignment as a technical specialist within the battalion's weapons section. This new role involved evaluating captured enemy equipment, developing countermeasures for enemy defensive techniques, and training other Marines in improvised weapons construction. Washington's practical experience and intuitive understanding of mechanical principles made him uniquely qualified for this specialized position. The strategic implications of Washington's innovation extended beyond immediate tactical applications. Military planners recognized that the Pacific War would continue to involve assaults against heavily fortified positions, and effective cave suppression techniques would be essential for maintaining offensive momentum. Washington's demonstration that effective weapons could be improvised from standard field equipment provided commanders with additional tactical options for future operations. Intelligence analysis of enemy positions cleared using Washington's incendiary launcher revealed important information about defensive construction techniques and ammunition storage practices. The sustained burning effects of the grease mixture often penetrated deep into cave systems, providing insights into tunnel layouts and defensive preparations that would have been difficult to obtain through other intelligence-gathering methods. The success of Washington's improvised system influenced procurement decisions for future Marine Corps equipment. Quartermaster organizations began including additional hexamine fuel tablets in standard field rations, recognizing their potential dual-use applications. Signal units started carrying extra magnesium ribbon for use in improvised ignition systems. These seemingly minor changes in supply procedures reflected the broader impact of Washington's innovation. Training programs at Marine Corps installations in the United States began incorporating instruction on improvised weapons construction based on Washington's documentation. New recruits learned to recognize opportunities for field improvisation and received basic instruction in the engineering principles that made such innovations possible. This training ensured that Washington's techniques would be available to future generations of Marines. The industrial manufacturing capabilities that Washington had observed in Detroit proved directly relevant to his military innovation. His understanding of metallurgy, combustion dynamics, and mechanical systems provided the theoretical foundation for techniques that appeared to be purely practical in nature. This connection between civilian industrial experience and military innovation highlighted the importance of diverse backgrounds within military organizations. Washington's correspondence with his family in Detroit provided detailed descriptions of how his pre-military experience had prepared him for combat innovation. His letters described the parallels between factory problem-solving and battlefield improvisation, emphasizing that both required systematic analysis of available resources and creative application of basic engineering principles. These letters, preserved in family archives, provide valuable insights into the mindset that enabled tactical innovation. The long-term impact of Washington's innovation extended far beyond the immediate tactical situation on Peleliu. Marine Corps doctrine evolved to incorporate systematic training in field improvisation techniques, recognition of innovation opportunities, and rapid dissemination of successful innovations. These doctrinal changes reflected the institution's understanding that individual creativity could have strategic-level impacts. Post-war analysis of Pacific theater operations identified Washington's incendiary launcher as one of the most cost-effective tactical innovations of the entire campaign. The system's low material requirements, rapid construction time, and high tactical effectiveness made it an ideal example of efficient resource utilization under combat conditions. This analysis influenced post-war military planning and equipment development priorities. Washington's military service record documented his progression from private to sergeant during his time in the Pacific, with specific recognition for his technical innovations and leadership in weapons development. His performance evaluations consistently noted his ability to solve complex problems using available resources and his effectiveness in training other Marines in advanced techniques. The scientific principles underlying Washington's innovation became the subject of formal study at military engineering schools in the United States. Physics and chemistry instructors used his improvised launcher as a case study in applied thermodynamics, ballistics, and materials science. These academic studies helped refine the theoretical understanding of the combustion and projection processes that made the system effective. International military observers who studied Pacific theater operations took particular interest in American field improvisation techniques, exemplified by Washington's innovation. Allied forces adapted these techniques for use in other theaters, while post-war military exchanges spread knowledge of improvised weapons construction to friendly nations around the world. The medical implications of Washington's incendiary system became apparent as combat medics treated personnel exposed to the smoke and heat effects produced by the burning grease mixture. Medical officers documented the physiological effects of exposure and developed treatment protocols for both enemy personnel and friendly forces who might be affected by the weapon's use. Washington's personal courage in developing and employing an untested weapons system under combat conditions demonstrated the type of initiative that Marine Corps leadership sought to cultivate throughout the organization. His willingness to take calculated risks based on sound engineering principles provided a model for other Marines facing similar challenges in their operational environments. The tactical flexibility provided by Washington's improvised system proved especially valuable during the dynamic phases of combat when planned fire support was unavailable or ineffective. Machine gun sections equipped with the capability to construct incendiary launchers could adapt to unexpected tactical situations without requiring additional resources or support from higher headquarters. Quality control procedures for Washington's improvised projectiles evolved through practical experience during subsequent combat operations. Marines learned to test fuel mixture consistency, verify projectile construction integrity, and calibrate propellant charges for optimal performance. These quality control measures ensured reliable performance when the weapons were needed most critically. The environmental impact of Washington's incendiary system remained minimal due to the biodegradable nature of the grease-based fuel mixture and the limited quantities of materials involved in each projectile. Environmental considerations were less prominent in wartime decision-making, but post-war analysis confirmed that the system produced no lasting ecological damage to the areas where it was employed. Research and development efforts inspired by Washington's innovation led to the creation of purpose-built incendiary launchers that incorporated the same basic principles with improved materials and manufacturing techniques. These production weapons retained the simplicity and effectiveness of Washington's improvised system, while offering enhanced reliability and standardized performance characteristics. The training program that Washington developed for teaching other Marines to construct and operate improvised incendiary launchers became a standard component of advanced infantry courses throughout the Marine Corps. His instructional techniques emphasized hands-on learning and practical problem-solving, reflecting his own background in industrial training environments. Recognition of Washington's contribution to Marine Corps tactical innovation came through formal citation in official histories of the Pacific Campaign and inclusion of his techniques in standard operating procedures for infantry units. This official recognition ensured that his innovation would be preserved and transmitted to future generations of military personnel. The economic analysis of Washington's system revealed extraordinary cost-effectiveness compared to conventional weapons designed for similar tactical applications. The improvised launcher could be constructed for a fraction of the cost of purpose-built weapons, while delivering comparable tactical results. This cost analysis influenced military procurement decisions for decades after the war. Washington's post-war career in civilian industry built directly upon the technical skills and problem-solving abilities he had developed through military service. His experience with improvised engineering solutions made him valuable in manufacturing environments where creative problem-solving was essential for maintaining production efficiency. The documentation that Washington created for his improvised weapons system became a classic example of technical writing under adverse conditions. Military technical schools used his field manuals as models for clear, concise communication of complex procedures. His writing demonstrated that effective documentation could be produced even in combat environments. International recognition of Washington's innovation came through inclusion in foreign military training programs and technical journals that studied American tactical innovations during World War II. Military engineers around the world studied his techniques as examples of effective field improvisation using commonly available materials. The psychological profile of personnel capable of successful tactical innovation, as exemplified by Washington's experience, became the subject of military psychology research aimed at identifying and developing similar capabilities in other service members. This research contributed to improved selection and training procedures for technical specialties throughout the armed forces. Washington's legacy in Marine Corps innovation culture established precedents for encouraging and recognizing individual initiative in solving tactical problems. His example demonstrated that effective solutions often emerged from the creative application of basic principles rather than from sophisticated equipment or complex procedures. The industrial mobilization that supported American forces in the Pacific Theater provided the material foundation for innovations like Washington's improvised launcher. The abundance of high-quality field equipment and rations made such improvisation possible, highlighting the connection between home-front production capabilities and battlefield effectiveness. Tactical lessons learned from Washington's innovation influenced the development of close support weapons that would be used in subsequent conflicts. The principles of sustained suppression, area denial, and rapid deployment that characterized his improvised system became standard requirements for new weapons designed for infantry support roles. The communication network that spread knowledge of Washington's innovation throughout Marine Corps units demonstrated the importance of informal information sharing in military organizations. Technical innovations often propagated through personal relationships and unit exchanges rather than through formal channels, highlighting the value of professional networks. Quality assurance procedures developed for Washington's improvised projectiles established standards for field-expedient weapons that would be applied to other innovations throughout the war. These procedures balanced the need for reliable performance against the practical constraints of combat manufacturing conditions. The metallurgical analysis of Washington's modified machine gun components provided insights into the performance of standard infantry weapons under extreme conditions. This analysis contributed to improved design standards for subsequent generations of automatic weapons intended for sustained combat operations. Training documentation produced by Washington and his colleagues became the foundation for comprehensive field manuals covering improvised weapons construction and employment. These manuals provided standardized procedures that allowed widespread adoption of techniques that had been developed through individual initiative. The strategic impact of tactical innovations like Washington's launcher demonstrated the cumulative effect of individual initiative on campaign-level outcomes. Small-scale improvements in tactical effectiveness, when multiplied across entire theater operations, could significantly influence the speed and cost of achieving strategic objectives. Recognition programs established by Marine Corps leadership to identify and reward tactical innovation drew directly upon Washington's example as a model for the type of initiative that should be encouraged and supported. These programs institutionalized the lessons learned from his experience. Post-war analysis of Pacific theater logistics revealed how innovations like Washington's launcher reduced the burden on supply systems by maximizing the utility of existing equipment. This analysis influenced post-war military planning and equipment standardization efforts aimed at improving operational efficiency. The scientific education that Washington pursued after the war, supported by veterans' benefits, built upon the practical engineering experience he had gained through military innovation. His post-war academic achievements demonstrated the potential for military experience to provide foundations for civilian technical careers. International military cooperation programs established after the war included technical exchanges focused on field improvisation techniques exemplified by Washington's innovation. These programs spread knowledge of effective tactical innovations to Allied forces around the world. The philosophical implications of Washington's innovation, that effective solutions often emerged from creative application of available resources rather than from sophisticated technology, influenced military thinking about the relationship between equipment sophistication and tactical effectiveness. Quality control standards developed for Washington's improvised weapons influenced post-war manufacturing processes for purpose-built military equipment. The emphasis on reliability under adverse conditions that characterized his field innovations became a standard requirement for military specification equipment. The environmental considerations that guided Washington's selection of materials for his improvised launcher, biodegradability, minimal toxicity, and sustainable sourcing, anticipated later military concerns about environmental responsibility in weapons development and employment. Training methodologies developed by Washington for teaching improvised weapons construction emphasized practical understanding over theoretical knowledge, reflecting his background in industrial training environments. These methodologies became standard approaches for technical instruction throughout military educational systems. The cultural impact of Washington's innovation within Marine Corps traditions established a lasting emphasis on individual initiative and creative problem-solving that continues to characterize the organization's approach to tactical challenges. His example became part of institutional mythology that shapes organizational identity. Historical documentation of Washington's innovation provided detailed records that enabled subsequent researchers to understand the conditions that fostered tactical creativity. These records contributed to scholarly understanding of military innovation processes and the factors that enable successful adaptation under combat conditions. The technical specifications that Washington developed for his improvised launcher became the foundation for formal engineering analysis that validated his intuitive design decisions. This analysis confirmed that his field innovations were based on sound scientific principles, despite being developed without access to formal engineering resources. International recognition of Washington's contribution to military innovation came through inclusion in foreign military academies' curricula and professional military education programs worldwide. His techniques became standard subjects of study in courses covering military engineering and tactical innovation. The economic impact of Washington's innovation extended beyond immediate cost savings to include broader efficiencies in military operations that reduced the overall resource requirements for achieving tactical objectives. These efficiencies contributed to the sustainability of extended military campaigns in resource-constrained environments. Professional development opportunities that Washington received as a result of his innovation established career pathways for technically oriented personnel within combat units. His example demonstrated that technical expertise could lead to advancement and recognition within traditionally combat-focused military organizations. The safety protocols that Washington developed for his improvised weapons system became standards for subsequent field innovations throughout the Marine Corps. These protocols balanced operational effectiveness against personnel safety requirements, ensuring that innovation did not compromise the welfare of service members. Scientific research inspired by Washington's innovation contributed to fundamental understanding of combustion dynamics, projectile ballistics, and materials science applications under field conditions. This research advanced both military and civilian applications of improvised engineering techniques. The procurement implications of Washington's innovation influenced military acquisition policies that emphasized the importance of dual-use materials and equipment designed to support field innovation. These policies ensured that service members would have access to materials suitable for improvised applications when operational necessity demanded creative solutions. Quality assurance methodologies developed for Washington's improvised projectiles established principles for evaluating field-expedient equipment that would be applied to other innovations throughout the war and in subsequent conflicts. These methodologies provided objective standards for assessing the reliability and effectiveness of improvised solutions. The training infrastructure that evolved to support widespread adoption of Washington's techniques demonstrated the military's capacity to rapidly institutionalize successful innovations. This infrastructure became a model for technology transfer processes that would be used to disseminate other tactical innovations. Recognition ceremonies held to honor Washington's contribution to Marine Corps tactical innovation established precedents for acknowledging individual initiative in solving operational problems. These ceremonies reinforced organizational values that emphasized creative problem-solving and individual responsibility. The technical legacy of Washington's innovation continued through post-war military research and development programs that built upon the principles he had demonstrated in the field. This legacy ensured that the lessons learned from his experience would influence future generations of military equipment and tactics. International military exchange programs that included technical discussions of Washington's innovation fostered cooperation between allied nations in developing improved tactical capabilities. These programs created networks of professional relationships that enhanced collective military effectiveness. The industrial applications of techniques developed by Washington for his improvised launcher found civilian uses in manufacturing processes that required similar combinations of portability, reliability, and effectiveness. This technology transfer demonstrated the broader value of military innovation for civilian industrial development. Educational curricula that incorporated study of Washington's innovation provided case studies in applied engineering, creative problem-solving, and leadership under adverse conditions. These curricula prepared future military and civilian leaders to approach complex problems with the same systematic methodology that Washington had demonstrated. The documentation standards established through Washington's technical writing became models for field reporting procedures throughout the Marine Corps. These standards ensured that tactical innovations would be properly recorded and disseminated to benefit the entire organization. Strategic planning processes that incorporated lessons learned from Washington's innovation recognized the importance of individual initiative in achieving operational objectives. These processes ensured that strategic plans would account for the potential contributions of tactical innovations developed by service members at all levels. The psychological research inspired by Washington's experience contributed to understanding of the mental processes that enable effective innovation under stress. This research informed selection and training procedures for personnel assigned to technical specialties requiring creative problem-solving capabilities. Historical analysis of the tactical environment that enabled Washington's innovation provided insights into the organizational conditions that foster successful military adaptation. This analysis informed post-war military organizational development and leadership training programs. The material science principles that Washington applied in developing his improvised launcher contributed to understanding of how standard military equipment could be adapted for alternative applications. This understanding influenced subsequent equipment design and procurement decisions. International scholarly recognition of Washington's innovation included academic studies that analyzed his techniques from engineering, historical, and organizational perspectives. These studies contributed to multidisciplinary understanding of innovation processes in complex organizations operating under extreme conditions. The training methodologies that Washington developed for teaching his techniques became standard approaches for technical instruction in environments where formal educational resources were limited. These methodologies proved applicable to both military and civilian training situations. Professional networks that formed around the study and application of Washington's innovation created lasting relationships between military personnel, civilian engineers, and academic researchers. These networks facilitated ongoing collaboration in developing improved tactical capabilities. Quality control procedures that evolved from Washington's experience established principles for managing innovation in decentralized organizations where formal oversight was limited. These procedures balanced the need for standardization against the flexibility required for adaptation to local conditions. The environmental consciousness that influenced Washington's selection of materials for his improvised launcher anticipated later military concerns about sustainability and environmental responsibility. His approach demonstrated that effective tactical solutions could be achieved without compromising environmental stewardship. Technical documentation standards established through Washington's field manuals influenced military technical writing practices for decades after the war. These standards ensured that complex procedures could be communicated effectively even under adverse conditions. The cultural significance of Washington's innovation within African American military heritage highlighted the contributions of minority service members to tactical innovation and military effectiveness. His example provided inspiration for subsequent generations of minority military personnel. Research methodologies developed through analysis of Washington's innovation contributed to understanding of how practical engineering knowledge could be transferred between civilian and military applications. These methodologies informed post-war technology transfer programs. The procurement policies that emerged from study of Washington's innovation emphasized the importance of providing service members with versatile materials that could support multiple applications. These policies influenced military supply practices for decades after the war. International military cooperation programs that included technical exchanges based on Washington's innovation created foundations for ongoing collaboration in tactical development. These programs enhanced collective security capabilities among allied nations. The scientific principles that Washington applied in developing his improvised launcher became subjects of formal study in military and civilian engineering programs. These studies advanced theoretical understanding of the relationships between materials science, thermodynamics, and mechanical engineering. Educational programs that incorporated Washington's innovation as a case study provided students with practical examples of creative problem-solving under resource constraints. These programs prepared graduates for careers requiring innovative approaches to technical challenges. The legacy of Washington's tactical innovation continued through military traditions that emphasized individual responsibility for solving operational problems. These traditions ensured that future generations of service members would be prepared to contribute creative solutions when conventional approaches proved inadequate. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.